Good morning. My name is Vivek Narsimhan. I'm an assistant professor of chemical engineering at Purdue University, and today I'll be talking to you about some of the work I've been doing in collaboration with people in agricultural and biological engineering to understand the rheology of starch dispersions. In particular, we came up with a methodology such that if you know the starch type and the temperature profile, we can determine how do starch granules swell as a function of time, and hence determine how does the rheology change as a function of time during the swelling process. We'll be discussing this methodology in this paper. So starches are found everywhere in our daily lives, such as our food and drink, as well as animal feed and pet food. But it's also found in several industries, such as pharmaceuticals, as well as paper and paints. Now, in all these applications, the mechanical properties of starches and gels, starch gels and pastes, are very important for their functionality. They determine how we perceive texture in food, but they also are very important in materials processing for these other industries. Just to give you an idea how important the mechanical properties of starches are, there's actually an industry out there whose entire job is to take native starch granules and chemically modify them for the sole purpose of modifying their physical properties, such as their mechanical properties. The market value of these modified starches is about $2.36 billion a year in the US and about $9 million a year worldwide. So we see that industry spends a considerable amount of effort to modify the physical properties of starches so they can tailor its mechanical behaviors. But if you talk to people in industry, you find that they really don't use any physics-based models to predict the rheological behavior of starch dispersions. So we want to know is if we can actually develop a model that can predict the rheology of a starch dispersion based on its physical properties and its processing conditions. If we can do this, we can save industry a lot of time as well as a lot of money in materials development. So before we begin, let's just talk a little bit about what the structure of starch looks like. Here's just a microscope image of starch. And if you see here, you see that starch consists of discrete granules that swell above a critical temperature. Okay? So if you want to think about modeling it from a rheological perspective, you want to understand the rheology of a starch, of a suspension of granules. Now, if you want to understand the chemical makeup of the granules, there's a lot of literature out there. But if you cut open a granule, it consists of concentric regions of amorphous and semicrystalline polymers. The amorphous regions are linear chains of amylose, and the semicrystalline regions are branched molecules of amylopectin. Now, above this TG, water interacts with the amylopectin regions, and this is what causes the swelling to occur. Here's what the typical behavior of starch rheology looks like during granule swelling. So when you heat up a granule suspension, what happens is above a critical temperature, the granules start swelling and the viscosity increases. When the granules start breaking up, the viscosity decreases as shown here, and then amylose starts leaching out into this dispersion during the breakup process. Once you start cooling the starch after breakup, the leached amylose starts cross-linking and forming a gel, and this is why you start seeing the viscosity increasing again, and this is known as retrogradation. Now, these three steps of the starch pasting process have been described in detail by a lot of publications. What we're very much interested in is looking at the initial stages of this process, the swelling process, and trying to be able to connect all the experimental measurements that have been done so far to some type of unified theory. Now, in order to be able to describe the swelling process, what we need to do is first of all develop a kinetic model to describe how did the starch granules swell as a function of time. And then we need to be able to link how does the size distribution from the swelling model relate to the rheology. All right. So here are just the details of some of the experiments that we're going to do. What we're going to do is take a starch dispersion as shown here and heat it up to some temperature TF and then hold it at that temperature for a given amount of time. So during this process, the granules will swell and will create a paste. What we do is we take out the paste and measure the size distribution using laser diffraction, and then we measure the rheology as well of this paste, G' and G'. So in this process, what we can do is we can control the final temperature at which we heat this suspension, as well as the heating time. Here are the type of starches that we test. We test 8 different varieties of starches, of maize, rice, potato, and cross-linked maize. They represent a wide range of possible sizes of granules, as well as a wide range of different ratios of amylose to amylopectin. Right? So when we go through these type of studies, this is what we typically get if we're doing size measurements. Here's what the average size of a granule looks like versus holding time for different temperatures. And during each of these points, we can measure also the size distribution as well. So what we want to know is if we can relate all the size measurements that we've obtained so far to some type of theory. And in short, the answer is yes. We've published 3 papers to describe the swelling of starch granules, and the details are here. Suppose if we have a granule and it starts swelling, what ends up happening is water diffuses into the granule and it causes the network to swell. Hence, you can describe the swelling using polymer network swelling theories that were popularized by Florey and Reiner. Basically, the swelling of a polymer network is governed by 3 factors. It's governed by the enthalpy between the solute and the polymer network. It's governed by the solute entropy, which tries to promote mixing, as well as the stretching of the polymers, which tries to prevent swelling. Right? In order to use these type of Florey-Reiner theories, you need to know certain physical properties of the granule in order to predict its size distribution as a function of time. One of the parameters you need to know is the gelatinization temperature, which is the temperature above which the granule starts swelling. You need to know the enthalpy of gelatinization, which happens during the swelling process. You need to know the Florey-Huggins parameter below Tg, which is related to the second virial coefficient between the solute and the polymer network. And you also need to know the fraction of chains that are cross-linked in the starch network. Now, these 4 physical properties of the granule can be experimentally measured, and in fact, we did that by performing differential scanning calorimetry for these 2, and also static light scattering, for example, for this. But these physical properties also have been tabulated in literature for several starches, so you can also just look this up in several papers. But if you know these 4 physical properties of the starch granule, we can use now our Florey-Reiner swelling theories and look at, for example, how does the particle size vary as a function of time for different starch varieties. And we get quantitative agreement between the experiment and theory. We can not only look at average particle size, but we can also look at, for example, size distribution. And we see that we also get quantitative agreement between theory and experiment for this as well. Lastly, we've been able to basically convert the size distribution data into volume fraction that's occupied by the granule, and so we can plot, for example, the volume fraction versus time for granules as for different heating temperatures, and we see agreement between theory and experiments as well. So what we found is we have a methodology now to predict the size distribution of granules as they swell. So in principle, we should now be able to obtain the rheology since we know the volume fraction occupied at every instant in time. So here are just some observations of what we've done so far in our rheology measurements. Here's what the linear viscoelasticity looks like as a function of frequency for waxy maize rice at 80 degrees Celsius, so at every given temperature. And the top curves represent the storage modulus, and the bottom curves here represent the loss modulus. All right. So the main thing I just want to point out in this graph is that the storage modulus in these pastes are much larger than the loss modulus. So for all these situations, we're dealing with primarily an elastic suspension. The second observation I want to just point you out to is that if we suppose we take this storage modulus data G prime for all heating temperatures and all heating times, and we take all the data and then plot it against volume fraction. If we do this, we see that all the data will collapse onto a single curve, and the curves will look different depending on the different type of starch variety. So you get a different curve for example, waxy maize versus cross-linked maize versus normal rice. The big difference between the 3 things is that you see that the limiting value of the storage modulus at which it levels off is different depending on the starch variety. Okay, so we want to basically understand how you can predict this type of this limiting storage modulus. So we see that the storage modulus depends on the volume fraction. So the volume fraction really determines the rheology of suspension. But then this limiting storage modulus depends on the starch variety. So how does this depend on the physical properties of the granule? So in order to understand this, what we do is we look at theories that people have done in the past. If you have a granules that are swelling, in the high volume fraction limit, the rheology of the suspension is going to be determined by the contacts between the granules, which is determined by the contact modulus between the granules. Now, there's been several theories that have been published that list what is this limiting value of the storage modulus. And if you look at one of the theories, you see that this limiting value of the storage modulus scales as the solid-liquid interfacial energy density divided by the average swollen granule size, where this interfacial energy density is between the granule and water. This is true under the situation where gamma SL over R is greater than the bulk modulus of the granule, and there's several papers that seems to suggest that this limit holds. So if you know the solid liquid interfacial energy density between the granule and water, you can in principle predict what is this limiting storage modulus. And so what we did is we were able to measure this interfacial energy density. What we did is we took a glass slide, put a swollen starch paste as shown here, and then did contact angle measurements for two different liquids on the swollen starch paste. One for water, which is the polar liquid, and one for a dispersive liquid shown here. If you know the contact angles for both of these liquids, you can use a theory that's OWRK theory to predict what is the solid liquid interfacial energy density shown here for different starches. And if you know that, then you can now predict what is this limiting storage modulus shown here. Okay. So what we're going to do here is we're going to look at the G prime versus volume fraction for all different starch varieties. And now we're going to normalize this y-axis by the theoretical limiting storage modulus G naught prime, which depends on the solid liquid interfacial energy density between the granule and water. And if you go ahead and do that for all different starch varieties, you see that the data all collapses onto a single master curve for all different temperatures and all different heating times, as long as the granules don't break. So what this says is that it seems to suggest is that there's a procedure now we can use to predict the starch rheology as a function of time. If we know the temperature profile and the processing conditions, we can use our granule swelling theory to predict the granule volume fraction as a function of time. You can now use the master curve for each point in time. You can figure out for each volume fraction what does the storage modulus look like, and hence you can gather the storage modulus versus time. All right, and this is true this can be seen to be true for any starch granule as long as you know the physical properties of the granule, which are the 5 physical properties that we discussed in this talk. So we've done actually a lot of comparisons between experiment and theory to try to validate our methodology. Here we looked at normal rice heated under various different temperature profiles, and we looked at, for example, the storage modulus and the volume fraction from our theory versus experiment, and we get very good quantitative agreement. We also simulated some foods like pudding, which are just suspensions of normal rice, and looked at volume fraction and storage modulus during a heating profile, and we also get quantitative agreement. But what's more important is if you look here at a parity plot, what we've done is we performed experiments of heating different types of starches at different heating temperatures and heating times, and each point here represents a different experiment. We have y-axis is the predicted storage modulus for each experiment and the experimental storage modulus, and we see that we get very good agreement between the predicted and experimental modulus for all the different experiments we've done so far. So in conclusion, we have developed a methodology to predict the storage modulus versus time for a starch dispersion under an arbitrary temperature profile by using a polymer swelling theory combined with a master curve. I'd like to acknowledge my collaborators for their wonderful work during this project, and I'd like to acknowledge our sources of funding. I'm open to any questions.